Welcome to Read Science. I'm your host, Jeff Schallmeyer, and I'm here with my co-host, Joanne Manaster, and we're here to talk today with author Ben Orlin about his new book, Math with Bad Drawings, Illuminating the Ideas That Shape Our Reality. I have one over here. I don't know if you can see it. Anyway, Ben is familiar to many of us as the author of the blog, Math with Bad Drawings, but he might also be familiar to you from his writing about math in newspapers and online magazines, familiar names. He says on his blog that he likes math, jokes, and teaching, and it's evident from his work that he identifies more strongly as a mathematician than as an artist, and with good reason. About his book, I liked the blurb that used the word goofy to talk about it. Goofy seems honest and sincere to me, and his book was indeed honest and sincere and interesting, and I only found one error, I think. Anyway, welcome to Read Science, Ben.
Thank you so much. There's a beeping in the background. I'm going to have to stop. I timed this.
Do it.
So I'll pass the baton over to you, Joanne.
Yeah, I'm going ahead and we're waiting for Ben, and it's good to make the alarm stop, right?
Yeah.
So, well,
it sounded amazingly like a dot matrix printer, didn't it?
Yeah. My apologies for that. Yeah. So I'm doing some book events in North Carolina right now and in a hotel room, and luckily our noon start time happened to coincide with an alarm that would have been lurking in the corner and hadn't made a sound since I got here. And then
somebody was sleeping in or reminding when they need to get out of the room.
It was in my room, so it was in my locus of control. Thank you so much for the introduction and for inviting me. I'm excited to get to chat with you guys.
Yeah. Hey, so Ben, I loved your book. It was great fun. And I had so many questions. And generally in life these days, I have so many questions, which is good for a scientist. But since I couldn't decide which questions to ask, we're going to play a fun game with one of these fortune tellers. Maybe our audience remembers these as a child, doing a little origami and putting colors and numbers and things like that. So to choose our question today, we're going to let our guests sort of randomly, based on your preference, we'll randomly choose a question. So you can solve for X, either
Let's go with that one on the bottom. I like
you like this one, X to the third equals 27. So let's solve for X.
Right. So right to the third means times itself, 3 copies of the factor. So we're going to pick X equals 3, and then 3 times 3 times 3 is 27.
So that's 3. That means if you guys remember how to use these little fortune tellers, you open, close, whatever number they said. So 1, 2, 3. And then inside here, we have some shapes, and the shapes have the different number of sides. Hexagon with 6, a rectangle with 4, a triangle with 3, and a circle with 0. What number do you choose?
I know it's more work for you, but I like the hexagon.
Hexagon, 6.
Like, honeycomb beehive kind of thing. I like that.
Yeah.
I thought sure it would be a circle.
1, 2, 3, 4, 5, 6. And this is the last one. Oh, we're back at the same. So choose your favorite shape. Maybe
we'll go with Jeff this time. Go with the circle.
Circle, okay. And I'm going to open that. And the question I am asking you is, this is a good place to start. Who is the audience for this book? You have humor, you have drawings, and you have excellent math description. Is it for kids? Is it for grown-ups? Is it for the disenfranchised grown-ups?
Yeah, that's a good question. Yeah, I've gotten there. And as I was working on the question, I would get that. I wound up giving a different answer to everyone I would talk to, where I would try to gerrymander my answer to say, well, you're the audience, whoever it is that I'm speaking with. One thing that it seems to be working a little bit, just messages I'm getting from people on Twitter as kind of a family book. I've gotten messages from adults who are curious about math, but maybe don't have a lot of professional experience with math, haven't thought about it since school, or from teachers who are thinking about math every week. But a lot of them are saying they picked it up. I wrote it for adults thinking it would be a grown-up book, but then it has lots of silly pictures in it of people with like giant eyes. And so actually, I'm getting a lot of messages people be like, oh, well, I got it for myself, but then my 10-year-old just won't put it down, or my 13-year-old was reading the Death Star chapter, or so I sort of like, I don't know, I like the idea that it can be kind of like a family film, but as a cartoonish book.
That's great. I found myself laughing through this book.
No.
Like puns and jokes and references to things that I wouldn't expect. although there's math in everything. So
yeah, no, I appreciate that. Yeah, I think as a teacher, I aim for getting a lot of sort of nervous laughter from my students. Pitying laughter, I think, is one that it's just when you know that they're not that I need to be clever, but that they sympathize with my efforts at it.
But I would point out, because we like to do this, we like books that are fun to read and don't shortchange the science, or in this case, the math, because as much fun as it is and as amusing as the drawings are, there is actual math going on in here too that's pretty easy to swallow, but also, not to be patronizing thing, but correct and to the point and carefully done and precise. And I think that's a great accomplishment.
Yeah, no, I really appreciate that. Yeah, I know that when people, when a sort of a mathematically sophisticated reader reads about mathematics that they know, you can't turn it off. There's just this thing going through your head where you're checking and sort of like, is that right? Is that right? Yeah, that checks out. And it's easy to sort of, in trying to popularize something or trying to share an idea, to say something that's just a little bit oversimplified or a little bit off. So I was trying to, in my own brain, I was sort of trying to turn on and then turn off that feature.
But sometimes I'll hold even popularizers to a higher standard, because they're talking to people whom I think don't really know how to judge what they're saying and can be very impressionable. So I judge precision, and in particular, I want the author not to say anything misleading that the naive reader might get the wrong idea from. And so I give you however many stars is necessary to say, no, I think that was a very good job of being on point without being all those things that people would fear from a math text.
Yeah, no, I appreciate. I'll take whatever stars you have to offer.
Yeah. Okay. I've got quite a few over here. I'll give you some later.
Okay. I'm going to let you keep talking because I made a mistake. The link that I sent to our audience, they're not here because it's the wrong link. So I'm pushing out a link right now. Okay. Sorry.
I want to. There's several things, and I want to ask about the table of contents first, which had two parts. First part, I'll get to in a minute, because there's some profound questions there that are very interesting. And the second one was like the math stuff that you chose to talk about. Yeah. Geometry, probability, statistics. I loved steps and sensitivity. I did some chaos stuff, but sensitivity is a nice thing. And so the simple question is like, why did you choose those? I'm thinking I know, but
yeah, no, it's a good question. I mean, basically, I had sort of three criteria, and they weren't criteria that I had at the beginning when we started to outline the book, me and my editor together. But what the criteria that emerged were basically, the topics needed to be mathematically rich, so there needed to be real interesting mathematical ideas there. Needed to be accessible, and ideally sort of accessible from the ground floor. So not something where, like distributions in probability are a really interesting topic. I don't really talk about it. And in fact, in one of the chapters, sort of go to some lengths to avoid talking about distribution, because it's just not a ground floor topic. It's that's 3 stories up in the building.
Yeah.
And then the third one, which was much more my editor applying some pressure there, but I think correctly, was to make sure that everything had some connection to human or physical reality. There are lots of beautiful mathematical topics that are just lovely in their own right. And there have been many wonderful books written about them, but this book, as it took shape, became a book much more, about the relationship between mathematics and the physical reality where we live.
Because you specifically wanted to make those connections and have examples from things that seemed familiar from everyday, like baseball statistics and insurance companies and stuff like that. And those are all good examples. But there's been editorials and a bit of a movement lately that I don't know where I come down on it quite yet, of saying, let's get rid of algebra and all that crap in high school and teach probability and some things anyway. Was there any of that in there too, that in some ways this is really useful concepts to have to get through life?
Yeah, I think that's part of it. I mean, I definitely wouldn't want to shortchange algebra. The algebraic skills that you develop in middle school and high school are important for opening doors to other mathematics. But I would definitely join the chorus on probability and statistics being totally essential branches of mathematics. And that's why it winds up being 40% of the book there's a section on probability and a section on statistics, which time was he was just last night, he was sort of asking me, he was like, it's math, but it's a little funny because it's not a particular topic in math. It's not focused on one topic, but it also is not a complete overview of all of mathematics. There's not much algebra in the book. There's no trigonometry. There's a chapter on triangles, but not really there's no sum.
But some geometry as far as a practical thing that lays some groundwork for later conversations, right?
Yeah, and I think yeah, exactly, yeah. So hopefully chapters like that can kind of can open some doors to interesting ideas, and also it's just the checklist of things I wanted each chapter to do was long enough that it was nice to have all of mathematics to pick from, where I could say, okay, well, let's look over here. Here's the topic that's accessible and interesting and mathematically rich.
But always, like you said at the beginning, that you said, I love this. That's math for you. It connects far-flung corners of life like a secret system of Mario tubes. And so always there was this how to draw in, how to pull in familiar things from the real world and not get too arcane.
Yeah.
The other part, which is really tricky to get at, but is really important, was in the beginning of the book, you had a couple of short chapters like how to think like a mathematician and what students really see. And those are very illuminating. And I wrote down 3 things, I think, that I'd like to hear a short disquisition about. A great mathematician can think slowly. And this was by a lovely anecdote about the student who asked you why then tests are timed, which I thought was a very deep question, really. But
yeah, no, it is. Yeah. There was just on Twitter the other day, a mathematician, Keith Devlin, who's written some nice popular mathematics books, was saying with certitude that there is no role for timed tests in mathematics education anymore. Joe Bowler is a mathematics educator, professor of education, who's talked about similar things. I mean, I think there's a reason we do timed tests, which is basically that you only got so much class time. That's what it comes down to. And it's funny how, I think about this a lot as an educator, the way that little logistical features of education, the fact that we've got finite time and finite resources there in the classroom, and the fact
you have to assign grades.
Exactly, yeah, that we want to assign in grades so that students can sort of be funneled through this system. The fact that there's one of me and 25 of them, and that's just an economical way for us to set up schools. All these features, which have nothing to do with mathematics itself. There's nothing intrinsic about those features. It's just that's what's convenient for a society that's setting up schools. And then those things become features in the student's eyes. They become features of mathematics.
Yeah.
So, you got 40 minutes for a lesson. So you write a 40-minute test. It's not like 40 minutes is a magic amount of time during which mathematics can happen. It's just.
I've found myself telling people who find some popular science books even, slow reading, and they internalize it and feel like they're just not smart enough to get things. And I tell them that they're not novels, that sometimes they need slow reading because there are ideas that take time to work in. And I felt like there was some relationship with that when you talk about mathematicians think slowly.
Yeah.
That there's this idea of, there's this idea of what you're about to tell me. What does it mean for a mathematician to think slowly?
Yeah, reading is a good one. That's something that I've thought about, because my wife and I did our undergraduate work together. She's a mathematical researcher now, and she's a much better reader of mathematics than I am. Obviously now that she's deep into a research career, but she always was. I was a good lecture listener. I could sort of pick up math when people were explaining it in person, but to read mathematics takes extraordinary patience. It's much more like poetry than it is like.
Well, the way a lot of my college math books were written is exceedingly slow and weird magical stuff. A mathematician has the patience to reach simple answers, and that, since I'm a scientist, that sounded very familiar to me, and I think that's going to surprise a lot of your readers, I think, who aren't familiar with sciences and math.
Yeah, I think it's definitely, if you see math in movies, it's all like these extraordinarily ornate equations covering the entire whiteboard. And I think this is stepping outside my expertise, but Einstein, when he sort of originally understood the relationship between energy and mass. This is more your neck of the woods. But that he formulated that equation a few different ways with different notation before settling on E = mc squared. And
the naive perspective about pursuits, math, science, even music, by people who don't pursue those things, is that the more complicated they are, the better an example they are. And the people who do that, we know that. It's like, no, Paul Dirac is a famous example of saying, no, I know this is wrong. It's not beautiful enough, this equation. Striving for simplicity. And you hear it when Feynman says something like, you know, if it's not simple enough, you can explain it yet to someone, you don't really understand it. And there's some feeling that profound understanding comes with seeing simplicity. Maybe it's a Buddhist sort of thing or something.
Yeah.
But mathematicians don't write, prove theorems and things and trying to make them as complicated as possible.
Yeah, no, yeah. I think the complication is like not necessarily, but in some ways it's the effort. The complication is like the sweat and the moving this around and the scribble outs and that's what brings the complication. And then ideally the final product is something very streamlined and reduced to its simplest, most straightforward terms.
Because it can take a lot of work to get to the simple.
Yeah, it can take ages. Yeah. There's this is something, right, again, from my wife that I've sort of gotten a sense of. But when she reads literature, she finds there's often, there's been this long, difficult, outstanding problem. Decades go by, centuries go by, maybe, and no one's got a proof. And then finally, someone comes up with a proof, and it's this really technical, intricate thing. And then you give it a few years, and somebody reads that, and now that they know it's true, they're able to kind of pare away some of the excess branches. And within a few more decades or a few more years, you've got something really nifty and brief and clear that you never could have arrived at as the first step, but it's you get something down, almost like writing, or you write a first draft and it's a mess, and then you kind of pare away and you cut and you find the truth there.
Simple is hard to find, and it makes me think of anyone who's written a research paper for a journal. The naive person will say, "Oh, that paper is only 3 pages long," and the professional says, "Boy, is it hard to write that short a paper. It takes so much work."
Yeah.
So,
is that true in biology too? Oh, sorry, I didn't mean that.
Well, I was sort of going to lead into this, that you have a whole chapter on science, how science and math see each other.
Yeah.
And I thought, well, you might as well address that now.
Yeah. I think, can I ask you first, actually, is yes. So that pattern, because I know it's physics and math, it seems like that's true, where you have original research often has this incredible complexity to it, and then over time it gets pared down and simplified.
Yes. Yeah. Oh, yeah, definitely. And, that we're all building upon what someone else has said. And it was, we didn't quite understand until we started to have more research projects that elucidated or made it clearer. So, yeah, I'd say it's the same. It's probably the same pattern across most science.
I think you can see a lot of that in the way that current biology is going. It's like it keeps sort of working its way, and here's some. It's like this helps me understand and I can clarify here, and things get simpler and clearer. And there's some stuff that's happened with I don't know, epigenetics or evo-devo, or now molecular genetic editing and things that have gotten amazingly simpler and easier to understand than they once were.
So why don't we go ahead back to that chapter about science, how science and math see each other. That was one of the choices in the fortune teller.
You don't want to bring back out the fortune teller itself?
No, I could, but that's okay. I only wanted to do that once.
Math and science, right? I think of them as this is something I've been talking about, actually, as I'm doing book events. That's sort of the chapter that I've picked to share with people in person. And so, what's the difference between math and science? I think how science sees math is the narrative that tends to dominate. So basically, science is out there trying to solve problems. Science is having these adventures and is trying to make predictions and do things. And then mathematics provides tools. Mathematics is this set of techniques that helps you do whatever you're trying to do as a scientist. And I think that's the analogy I give is like, you got James Bond, which is science. And then you've got mathematics is like Q at the beginning of the film, equipping James Bond with all the little gadgets he's going to need during the film. And I think that's sort of like the standard narrative you get as a student. The mathematics-centered narrative is a little weirder and more experimental, where basically mathematics sees itself as this kind of artist. And when I talk to mathematicians, they're much quicker to compare their work to art than they are to or to philosophy sometimes than they are to science. There's people on the borderline, obviously, but and so what does mathematics do? It takes scientific ideas or other sorts of ideas and then looks for logical extensions that may not have anything to do with physical reality. With like a classic, I think it's in the chapter, but a classic example is like any point in space, right? Like on the screen right now, right? Two-dimensional, but so you can specify. I got to think about the mirror image before I put my origin. Is that the right origin, or should I be on the other side?
The other side.
Oh, the other side. Sorry, yeah, that's all mirror. Anyway, so here's the origin, and then right, like you can specify any point on the screen like this with some number of steps that way and some number of steps that way. And if I want to do it in 3 dimensions, then I just need to add a third number, right? And the mathematical mindset is like, well, what if there were a 4th number?
Yeah.
And the scientific mindset is like, there's not a 4th number. It's a dumb idea. Like where is that going to lead us? But because it just doesn't seem to correspond to our physical reality. But it leads to all this beautiful, interesting mathematics, just extrapolating, and you get hypercubes and kind of beautiful 4-dimensional mathematics.
But then all this beautiful abstract math keeps getting sucked into physics somehow. And I'm working up to my profound question, but it's like, oh, here's Einstein saying, oh, I don't know, I just can't make this work out. And here's someone who is saying, oh, let me show you these cool Riemannian manifolds over here. And before you know it, you've got general relativity. And it looks like, and this may be the after the fact narrative, it looks like, oh, this was just waiting to be the natural explanation for this. And for most physicists that I know, it always seems not troubling, but one of the deep mysteries is, why in the world does math keep working so well for physics?
Yeah, I have no idea.
It's got something to do with our brains. And sometimes I think, maybe any tool that sort of works kind of like that might be put to use. But boy, it really seems like serendipity is trying really hard sometimes.
Yeah. One of my favorite essays is Eugene Wigner has this essay, "The Unreasonable Effectiveness of Math and Natural Sciences." Yeah, which I think sort of captures the title. I like just the unreasonable. I think it's the word, unreasonable effectiveness, which is exactly this: that mathematics, right, through this process of extrapolation, takes ideas that are anchored in reality and totally cuts off that chain, so the anchor drifts away. And now mathematics is just running off with these bizarre, hypothetical, theoretical, nonsensical sometimes questions, which then turn out to be totally useful for scientists down the road.
And you can think, okay, counting numbers and addition and subtraction, they're part of the world, maybe that. But by the time you get to group theories and things, and suddenly those become applicable to critical phenomena and particle physics, like, how does that even, that's totally unreasonable. How does that come about?
I agree. Yeah, it seems like it's something about logic, right? That fundamentally what mathematics is it's it's a structure of logic, right? It's
patterns, the way constrained systems fit together, or something.
Yeah, exactly. Yeah. Somehow this like cosmos we inhabit does follow logic, right? If A then B, so if A then B, I don't know. There's something about the persistence and the inevitability of logic that means that if you're just chasing a logical path, even though you can't see where it's going to lead, it sometimes does lead someplace worthwhile and real.
I think it feels to me like both mathematics and the universe are largely made up of emergent properties, and maybe they just share an origin or something. I don't know. Save us here, Joanne.
Yeah, I'm not going to be able to save you on that. Actually, I have a question because so, as Jeff knows, and we keep threatening to bring my kids on Read Science in an episode. So I have 4 kids. 3 of them are in the hard math, hard sciences, I should say, with a lot of math. And one thing I noticed, so I'm a biologist. So biologists are sometimes, not always, sometimes known for being math adverse. And then, of course, things like physics and engineering require a lot of math. And so my 3 kids, I've got an atmospheric scientist, a hydrologist, and a geologist. And the other one is a Spanish language major. But she was also good at math. We can thank their dad for that more than myself. But for myself, I loved geometry and I loved statistics, and I did very well in both of those. But when algebra was a struggle, calculus was a struggle. Do you see these kinds of split? Whereas my kids who love calculus and differential equations, they aren't fans of geometry. Do you, as a teacher, do you ever see a split in ways of thinking of math? And
yeah, no, absolutely. Yeah. One of the things I found daunting about writing this book was that it was going to be it was math math with bad
Just
drawing.
math.
And my friend was like, what is there? I wound up writing a lot of paragraphs and pages that didn't make it into the book, but basically to the point of like, math is not one thing. Math is a whole variety of things. In the same way that science is not one thing, or the humanities is not one thing. Math is this incredible variety. So yeah, exactly the things you're mentioning. I mean, even the two that you mentioned as particularly enjoyable for you, like geometry is one tradition within mathematics, and then statistics is its whole other tradition. And then trigonometry is this third path, and calculus has its own, and they all intersect in complicated ways. And there's pure mathematics where you're just solving puzzles for their own sake, and there's applied mathematics where you have much more scientific concerns trying to take these abstract techniques and bring them back down to reality. And definitely, when I think about my students, everyone has their own profile of what they find enjoyable or easy, which for a lot of students are sort of the same. What comes easily to you is what's enjoyable, but not always. Sometimes I'll meet students who there's something that they have an easy facility with, but actually they're really curious about some other thing that they find harder. For myself, stuff that's very tactile and visual, which I know a lot of my students, that's what they connect most easily with. I find really hard. I don't know. Someone showed me this trick earlier this year, a really cool trick with a piece of paper that you fold up and you put some paper clips on it and you kind of pull the piece of paper apart. Yeah, it's really, and then the paper clips wind up linked. And I had to like 10 minutes. I just didn't get it. I was like slowly pulling them apart, just watching. I realized not only do I not understand that trick, I don't really understand paper clips. I was realizing, I was like, pick up paper clip product. How does that work? So yeah, definitely everybody's got their own things that they're curious about.
Not really a topologist.
Right. Yeah. I need to find a topologist to walk me through that one.
When you were talking about how students see mathematics, and I know I've seen how students see physics too. That students, early on, students at least, tend to see mathematics as this sort of alchemical trick. It's a thing, and if you say the magic formula right and identify the right things, the right variables and knowns and unknowns, you'll get the right answer and the points are yours. And how mathematicians see it started to give a very good flavor for how a mathematician or a scientist, I would say, look at a problem and sort of start taking it apart, and they start telling themselves stories about it as a way to, I don't know, twist it around, look at it, taste the little bits. And I think to the student, that's probably a waste of time. When are we going to find the knowns and unknowns and plug them in? But that's where the understanding comes from. And so the big question is like, when can students start learning that? How do they learn that? How do you get that across to them? Because that is so important. And if people don't get there finally, math is going to stay another thing.
Yeah. The different teachers have different philosophies on that. I've heard from lots of different people who have different approaches. My feeling is generally that I always worry about introducing a symbol or a type of formal manipulation of symbols before it has meaning for the students. Because I think what winds up happening is if you learn it as a form of choreography, that's sort of how I think of it. It's like basically like, here are the dance moves. I know you can't hear any music because it's all sort of nonsense, but like it's sort of you're performing this dance for an audience of one who is the teacher, and then if you do the dance correctly, you get points, and that's sort of what it feels like.
But then there's a bit of fake it till you make it thrown in there too, and I have the feeling that many students aren't ready to synthesize things into more abstract ideas until they're 25 years old, maybe, or something.
Yeah. So a lot of colleagues that I love take more of that view. That what you're going to do is you're going to go in and you gotta learn some technical skills, and then later, once you're adept with those and you don't have to be thinking as hard about them, they're second nature, then maybe you can go back and start to read it as language and start to apply some meaning to it. I've got colleagues I really love and admire who think about it that way and teach that way. It's never quite made sense to me. For me, it's always been the case that when I'm introducing a new term, a new anything, I want students to understand what it is that they were looking at, and then learn to manipulate it. And in particular, what I usually worry about is that if there's no understanding at the beginning baked in, it's really hard to come by later, because it's hard to create a need for the students if the students can already sort of perform the dance.
Yeah.
And then you try to turn on the music, and they're like, "Oh, turn off the music. It's distracting. I'm trying to dance over here." So it's like it's hard to later bring the meaning in when it wasn't. I mean, meaning I think is it's not the icing on the cake. It's the thing that makes the cake rise.
Although I think the way you've written the book suggests that you're not entirely bottom up from this either. And students, even if they don't synthesize it that way, still will like to talk about or hear about the sort of top-down abstract ideas and how things fit together. I've had some teachers always like, and then someday you'll see that this happens and there'll be a system that does this where these things fit like this. And it didn't make any sense to me yet. I saw it later, but it was like, wow, it's like this big shiny Close Encounters thing or something. And, it's going to be cool someday. And a lot of students seem to enjoy that as well. And you did some top-downing in this book, not just introducing.
No, definitely. I think bottom up and top down are interesting terms for it. I think, I guess I would describe my approach as sort of a mix. Not that you always need to start with super particulars and like very close inspection of some particular bit of algebraic notation, but more just that, algebraic notation, every bit of mathematical notation is a name for something. Mm-hmm. And then also the way it's designed, mathematical notation, is it's these names for things, but that there are rules you can just manipulate them by.
Yes.
In my general, I think, and this is a very broad claim, so it may not work in all particulars, but my basic philosophy is that before you learn the name for something, you should know, or as you're learning that name, you should know what it is we're naming. Yeah. Like there needs to be when we're talking about the sine function, one could learn the sign of lots of common angles before knowing kind of what sine means. But I kind of want, if we're going to be using that word, let's make totally clear we know what it means from the start.
Algebra is one of the worst for the alchemy aspect too, isn't it? It seems like it really is just rules for moving things around. Is the way it looks, but it's not, and that seems to be such a barrier for some people. Algebra seems to be a big dropping off place for a lot of people.
This is something I've been thinking a lot about this with my second book that I'm working on right now is due in a couple of weeks.
Good, excellent.
It'll be done on time. If my editor's listening, it'll definitely be done on time. Anybody else, we'll see what happens. So something I'm thinking about, like calculus is exactly this. And calculus is sort of a forerunner to that kind of, and in fact, kind of brought in this age of blind algebraic manipulation. There's a quote from Vladimir Arnold, who's like a 20th century Russian mathematician, where he says that Leibniz developed analysis in a form that was specially suitable to be taught by people who do not understand it to people who never will understand it. Which is like, as a calculus teacher, it was a bit of a but also I think does like the notation really, Leibniz really thought hard about that, and as algebraic notation developed, the point really was that there will be simple rules and you can just apply them as formalisms, and you won't necessarily like, and that's nice. I mean, if you're a common user of mathematics, like it's nice to be able to do it quickly and automatically and not have to think super hard. Like the original algebra was all this rhetorical algebra, where it's all sentences written out, and these long Arabic sentences. It was really hard to do.
All word problems.
Yeah,
exactly. Nobody sees English that way. They don't see words and letters as things that you move around according to some rules, and you get a novel. And yet the mathematical symbols they have trouble seeing as a way of expressing ideas.
Yeah, I've talked to some writing instructors who feel that students, again, it's partly because of the pressures of education, not as bad as it is in mathematics necessarily, but there's a little bit of like just kind of writing down and parroting back phrases that you've heard and what sounds like an essay, and sort of in a somewhat analogous way, I think, just sort of that language doesn't feel like something in one's control.
The typical sixth grade "what I did this summer" is pretty predictable, isn't it?
Yeah, sure,
Okay, that's a point.
Well, speaking of all of this, then there is, of course, the controversy: should we replace algebra in high school with stats? Because nobody's going to use algebra, but everybody could really use some stats, which I think is maybe not fair to ask a mathematician, but I think your opinion could be valuable.
Yeah, it's a good question. I think one of the things, right, like sort of top down, bottom up again, right, in a different setting here. But I think we tend to think of education as sort of outside of I'm not a curriculum writer or an educational administrator or anything like that. I'm a teacher and a writer. So as an outsider to that process, I tend to think of, my instinct is to think in top-down terms of like, well, curriculum designers choose a curriculum that is implemented in a school, and then so there's sort of a decision point at the top. But I think there's also in math education a lot of bottom-up forces, where, for example, why is calculus kind of the be-all, end-all? Why does math education always seem to build, especially in the US, it's not as true in other countries, I think, but why does it always build the calculus? I think probably there are some top-down reasons, decisions made at the college board or university admissions offices or wherever. But there's also this kind of bottom-up thing, which is students, they want to get into competitive colleges. They're looking for some kind of peacock tail that they can grow, some kind of signal of like, look, what a healthy, ambitious, smart student I am. And calculus and algebraically intense courses kind of serve that role. They let you prove your mettle as a high schooler. Not to judge either way, whether that's an accurate proof of one's mettle or not. But I think that definitely seems to be part of why. I mean, if you just ask high school students, why are you taking calculus? Like, I needed to get into the fancy college I want to go to. Yeah. So I think if there were, so a long way of saying, I think if we made top-down decisions to de-emphasize algebra, it's not obvious to me how the bottom-up forces would respond. You might, that said, I think, there's a lot in the Algebra 2 curriculum typically that doesn't strike me as super useful. Conic sections is something that's like, when I taught in the UK, they just like wasn't taught these like Cartesian coordinates for conic sections. And I was like, oh yeah, because it's like not that important.
But your first level algebra certainly helps.
Yeah, exactly. Yeah. So I think, the algebra of sort of lines, right? Like understanding lines in the coordinate plane.
I've always thought
that's really powerful.
Algebra is I posit the first place where people come upon and then start to learn how to manipulate abstract things. And I think that can be very valuable, because once you do that, there's no going back. You've learned another level of how to think about things, and you can ratchet your way up from there. And I've always thought that maybe calculus has a mystique just because its first name is the. What was that about? I never understood why it was always, this is the calculus.
Especially given that there are lots of other calculuses, right? I mean,
yes.
Calculus is a system of calculation.
Yes.
Right. So I may have missed this when I was in it. So those of you who've just joined, you probably joined because I sent out madly a thing saying our link has changed. Our link has changed. So thank you for joining us late. Be sure to catch the beginning, because we were playing with a fortune teller, paper fortune teller. So when you guys were talking and I was half listening, did you talk about the fact you don't have a chapter on prime numbers? Is this because you wanted the book to be as practical as possible, or I was like, where's the prime numbers?
I know. Yeah, that's totally fair. Right. That's, I mean, if you're going to write a book about like where the like I've got the copy here, like it's math, right? Like if you're gonna have math in giant letters, like how are you not talking about prime numbers? When I was sort of first outlining this with my editor and we were brainstorming ideas back and forth, my ideas tilted more towards kind of pure math, because that's what my background's in. Yeah. And she applied, I think correct, but I think the book came out much better for it, but I was applying some pressure of like, well, why? What does it cash out into? And so, I hope the book still has a flavor of what pure mathematics is about and pursuing ideas for their own sake. But I think to kind of speak particularly to the, I shouldn't even say it. It's not that pure math or prime numbers doesn't have a really cool role to play. It's just kind of in the shape this book took. It didn't really fit. Particularly because it was going to take a few chapters of developing the theory of prime numbers and the concept of prime numbers, and then after like 2 or 3 chapters of that, I could have gone to RSA encryption or some kind of cool real world application of prime numbers. But there just wasn't quite the rhythm that this book was taking on, which was much more like within each chapter you're going to get a new mathematical idea and it's going to pay out in some real world setting.
Okay,
which you did,
and then so the book ends up being practical and references to pop culture. And one of the practical chapters here is about the elections. And since we just had elections, I'm going to leave it. Your chapter is called One State, Two State, Red State, Blue State. And so you sort of start talking about democracy as a game of telephone. I'm going to let you choose whatever you want to talk about elections, since it's timely, if you don't mind.
Yeah, I find, right. Yeah. So the chapter one's being all about the Electoral College. Partly just because I find it really mathematically interesting. I mean, as much, I'm not a political theorist. I'm not a pundit. I'm not a politician. So so I can't really speak to the political issues that arise with a system like the Electoral College. But it's got really cool mathematical features, really strange mathematical features, and particularly it's not so much the weighting of the states, which is what people focus on a lot. The fact that Wyoming versus Texas is 3 versus 38 instead of 1 versus 36 or something, which is what it would be if you did it strictly in population terms. That's just actually not that meaningful in effect. It matters on the margins. But what really matters in the Electoral College is the fact that 48 out of 50 states are all or nothing. Right? There's it's Nebraska and Maine, which do it slightly differently. But basically, you win Ohio by 0.5%. Or you win Ohio by 60%, you win 80-20 in the biggest landslide ever. And it actually doesn't make a difference. As long as you cross that, you get Ohio's, whatever it is, 20 or so electors. And that makes for this really weird kind of jumpy system where you move a vote over here and now you haven't lost anything in this state, but you've suddenly won this state. And so it's this, it's got sort of lots of giant steps built into the system. Which just has is a funny mathematical property for an electoral system and interesting to think about and play with.
It defies expectations. Now that you're talking about it, because people tend to think that most things they encounter will be linear, and this is simply not.
Yeah. Oh, sure. Yeah, elections in general. I mean, this is inevitable whenever you've got a whole country trying to make one decision. Is you're going to have, say we had a popular vote for the presidential election, there would still be this crazy nonlinear jumping point where you go from,
Well, speaking of that, then there are questions like that have to do with, I don't know, combinatorics perhaps. Is there a fair way to vote?
Yeah, I think it seems like for designing a legislature, the political theorists, and again, this is outside my area of expertise, but they seem to all really like proportional voting. What we've got a district by district system, and it's all you got the most votes in that district and you win. So it's got, and that allows for gerrymandering, and it can create some weird effects where whereas proportional is just the natural idea that if you've got two parties and one gets 60% and one gets 40% of the vote, they get 60% of the seats, they get 40% of the seats. Whereas
dividing it by states or by the country, well, that's another matter. My other question was, is there a fair way to draw conditional districts, which has been a big practical question and has been seeing some changes in litigation in the last couple of years? But my again, very amateur understanding is that we've got some good metrics now for telling when a map has been very cleverly drawn by one side to give them enormous advantages, and that this is obviously something people. It's gerrymandering named after Albert Gary, who's governed my state of Massachusetts in the late 1700s, early 1800s. Right, it was a very old system, and part of the reason that it's become so relevant recently is that even by 2000, I don't think the technology was quite there to do it excellently. But by 2010, because it's every census, by then the technology had developed to an extraordinary point where you could gerrymander really, really well. You could do space age gerrymandering. But you also, conversely, you've had a recent case that overturned gerrymandering because the judges at a state Supreme Court said, we now have, and mathematicians who testified have said, here is a way to draw fair districts according to these criteria, and that did not exist before. And this underscores the point of your book that, it's like, oh, who would have thought that, I don't know, graph theory and mapping and all of these really abstract group ideas might show up in a Supreme Court decision.
My understanding is that
that's what they were waiting for. The judges apparently were waiting for a practical way to measure when something was wrong.
Yeah, that's right. Was this the Pennsylvania case?
I think it was, yeah. Yeah,
because Wisconsin also had some, there were some court decisions around it. Yeah, my understanding is that you've got, there's some really quite fancy ways of analyzing a map where you can go through and sort of randomly reassign districts to, or, what is the smallest, I forget what the smallest unit is called. like a constituency or something. But anyway, or a precinct. But so you can sort of randomly reassign precincts to the next elector and the next representative and sort of see what happens if you go through and do random reassignments. And if you go through and do some random reassignments and it turns out that that totally changes the outcome of the election, that's a sign that probably this map was very, very carefully and cleverly drawn to advantage one party.
Yes.
And then there's really simple metrics. So the efficiency gap is one that people like to talk about, and Moon Duchin, Tufts, and others have written and talked about.
The other nice thing from something we talked about is that these methods that the mathematicians are offering to the courts, that the courts are finding amenable, are pretty simple ideas. It's finally gotten simple enough.
No, that's exactly. The efficiency gap has that really nice feature that, like, basically the idea of the efficiency gap is the only votes you need are the ones that get you to a majority.
Yeah.
Right? So if there's a vote that in a district you lose, that didn't help you. You know, like if you get 48%, you lose to 52, like it didn't help you. And if you have 53%, those last couple percent didn't actually do anything for you.
Yeah.
So you basically call all those votes wasted, anything that's not just getting you to a majority, and then see which party's wasting a bigger percentage of their votes.
Yeah, and that gets it back closer to something that feels more linear than nonlinear, doesn't it?
Yeah, exactly. Yeah, and it's a pretty easy to draw, pretty easy to explain method of seeing how fair a map is.
Who's ever going to use math in their everyday life unless they become lawyers?
Or citizens,
Exactly. I wonder, when you teach and you've taught middle school, high school level, do you know that every time you teach this topic, whatever topic it is, the classroom's just going to be buzzing and happy and just like, oh my goodness, this is, we're so excited, or conversely, the one where everybody just goes.
I can almost hear my students chuckling in the background, like buzzing and happy. This guy, no way. It really depends on the group, actually. I mean, I've taught at two schools. One, I mostly taught 11th and 12th grade, some 9th and 10th grade too, in California, and then the other one was a school in the UK, and I taught 6th through 12 there. And it really depends on the group. It depends on the particular students. One thing that is a pretty good recipe for not a fun, happy time is math that they feel like they already know, but there's something else I want them to get out of it. And like that's just so, and I get why. I think about it as like, I don't know, like I go rock climbing sometimes. And if someone were to be like, okay, I know you're working on this hard rock climb that you think is challenging, but I want you to go back and do this one you find easy. Yeah. And I'm going to tell you you're doing it wrong. That sounds horrible. Like, give me a fun challenge. And so I get where students are coming from. So some of the work there is trying to take something old and familiar and dress it up so it doesn't feel old and familiar anymore, to give it a new spin or a new angle or some kind of new entry point. So that, one common one is when students have when students have been given, like we were talking about earlier, like a very thorough drill in how to, when they came up was, so actually solving linear equations is a common one. So you've got 7x plus 2 equals 23, and what's x? And I'd like students to understand this idea of an equation as a statement of equality. That we're saying 7 of the x's plus 2, that's the same as the 23 over here. Those are equal somehow. And like, what can you do? Well, you could take away 2 from this and take away 2 from this, and they're still equal. So now we've got 7x and 21. And so like sort of that like the same thing to both sides that math teachers love to talk about. But they've often got like a system where they're like, oh no, well, I just take the 2 and I change the sign and I move it over here, and now plus becomes a negative. And so, well, why did plus become a negative? And they're like, that's what happens. But if I try to just like head on teach them a different way of thinking about it, again, it's like telling them to go back to an easy rock climb and say, no, now this time hold your hand in this way you don't like, and do it again. So often it's trying to come up with different ways of framing the task.
And that's back then to trying to get them to take the equation apart, tell themselves a story, and taste parts of it, and they're just not in the mood for that, it sounds like.
Yeah, well, especially if it's one they can already do. It's like if they're used to a system that rewards them for getting the right answer and doesn't really give much credit or due to
they already know the magic spell for that one.
Yeah, exactly. Yeah.
Right. So now this I have to thank my daughter for providing this, although I've not taken advantage of this insight. My daughter, who's got a physics background and is working on her PhD, she's doing her quals, so shout out to her. Good job, good work today.
Horror stories.
Yes, it is. So But she always said, she goes, I sort of love 6-page math problems. And I just like must have looked horrified. And I said, why would you like that? And she goes, because when you get to the end of the page and the answer is not what it's supposed to be, she goes, you know, what you did wrong is somewhere in there. And that was comforting to her. And I thought, I never thought of it that way. But it you know, like to me, because I always thought when I got something wrong, it was some punishment from the universe, or I'm cursed, or, you know, something totally unscientific, like it. And it wasn't me. It wasn't my wrong thinking. It was, oh, I'm so bad at this, you know, where she just looks at it more, probably correctly, that, oops, something's wrong in here, but I can find it somewhere in there. And I don't know if this is very common with mathematicians. They just think, yeah, well, that's right. It didn't come out the way I hoped, or the answer book says it should. But we can fix that.
Yeah, well, I think her sentiment is probably unusual even among mathematicians and physicists.
Okay.
Taking pleasure in that is like, that's an extreme. I think my experience, and probably a lot of it, right, Jeff can chime in too, but like my experience, I think most mathematicians I know, is somewhere, right, if there's a continuum going from like pleasure and enjoyment of that to like what you were experiencing of sort of like a kind of fatalism and disappointment and like a punishing yourself for having gotten it wrong. I'd say most mathematicians are like just kind of in the middle with like, oh, that's frustrating. Now I have to go find where I lost that minus sign, or where I canceled something wrong. But definitely, I mean, your experience, I think, is really common for a lot of students. And I don't know, as a teacher, I always am looking for ways. I know there are lots of little ways that I'm setting up that expectation without even meaning to. You know, I just like the red pen has so many associations. And if I'm going through, and I'm just trying to give quick feedback because I don't know, I want to get on to plan my next lesson. If I'm just giving, you know, check marks and X's really quick, and I'm not even thinking twice. I'm just like, well, I just want to tell them which ones they should look at again. But that for a student, that can be like, there's a red X on my work. It's like that feels like such a devastating judgment.
Right.
When I was working on the microgravity experiment, it seemed profound when I realized there was a vast difference between the way a project manager and the scientist respond to the observation, oh, we've got a problem. The scientist is like, oh yeah, it's a problem. And the manager's like, oh my God, there's a problem.
So, you know, I wonder, I always wonder when I read books, like, was there a chapter that was much more pleasurable for you to write than any of the others?
Yeah, I think probably the most fun chapter for me was there's chapter 10 is called An Oral History of the Death Star.
Yes.
that was fun to write. Yeah, because
there's your drawing.
right. There's our advertisement for the Death Star. Yeah, because it's Star Wars is fun. Pop culture references are fun. And the Death Star being a sphere is like a fun. I don't know of other spherical space stations out there in fiction, or certainly not in you know, NASA reality. And so just getting to kind of like play with the idea of like, well, what would be the consequences of a sphere in space, and like having think about surface area, and you think about curvature, and so just thinking about some simple mathematical properties, and then on top of that, getting to like put all the quotations in the mouth of Darth Vader. It was just,
yes,
that was a very fun one to write.
Yeah, and you even have little drawings of Chewbacca. Ish,
yeah.
You know? I don't know. Are you breaking some copyright laws by drawing Chewbacca?
Yeah, let's not CC Disney.
To do that, you'd actually have to look more like him, probably.
There we go.
It's ish. Chewbacca ish. to describe symmetry was pretty clever, and yeah. So I think my kids are much better at math than I am, but I do need an opportunity to go look at this fun book.
Yeah, that sounds good. No, I mean, definitely, right. I mean, I think, right. I mean, it sounds like the two of you have sort of different relationships to math. Where Jeff, for you, it was like, you know, a central professional activity, and for you, like, it just hasn't been as central to your scientific career.
Right.
Yeah,
right.
I think
they make us take calculus, and they make us take the biology level calculus.
Yeah, they made us do it too, but
yeah.
Well, but ours was this special like calculus for biologists.
I've talked with people at a few universities where they're starting to do, so some innovative stuff with that, like that calculus for biologist class of trying to, right, you can sort of focus on biological examples, but also weave in other topics and kind of approaches.
Right, make it relevant, and I think that's important to every kind of teaching is, how is this relevant to you? In your book, you have practical things, like you talk about DNA inheritance. And, so as a biologist, I thought that was cool. And, but that's mixed in with a bit of probability there. How do these mathematical concepts apply to your life? But also, hey, let's look at math with this fun pop culture reference too.
So I hope I was sort of, when I was writing it, I was in my head kind of running through, I think, not you two specifically, but both like the sort of the angles you're coming from as readers, where I wanted it to be for someone who's had a long professional relationship with mathematics to still feel fresh and playful and silly and have new angles. And then for someone for whom math was sort of like kind of a school memory and just hasn't been relevant, and maybe not necessarily a happy school memory, to have it still be a playful, fun experience.
Why do people persist in so thoroughly misunderstanding marginal tax brackets?
I don't know. We had this problem this year. My wife did our taxes because she's a superhero, and then they sent us a message saying that we'd understated our income by X dollars, and therefore we owed 10x dollars as tax. Which this is impossible. She spent hours on the phone with the IRS, and finally got, I think, the fourth person she talked to said, "Well, one possible explanation is tax brackets."
No.
she was much cooler about it than I would have been. But she was like, "Well, and my understanding is that's not really an explanation because that's not how tax brackets work."
That's right.
But when even the IRS is having that problem, that's a widespread notion.
Yeah, and I think it's willfully misunderstood frequently in political discourse, but.
Hard to say. It was funny. One of the chapters I'm working on for my next book actually is about the Laffer curve.
Oh dear!
Famous sketch.
I'm going,
Which ruined most of the 1980s, really.
Right, I wasn't around during the Reagan administration. Right, I was more sort of in the tail end. So this is all more historical to me. But the Laffer curve, which I think, if you ask most academic economists these days, it's this idea. Right, well, you can read the second book too. But it's this idea that basically, so you take a graph. Am I doing this graph right? Is that?
Yeah.
Okay, cool. Yeah, the mirror is hard for me. And so the x-axis is tax rate in, I guess, some kind of simplified system where there's only one rate.
Call it tax burden or something.
Yeah, or tax. Yeah, it's right. It sort of depends. It depends on what you mean exactly. But yeah, exactly. And then the y-axis is just how much money the government collects.
Yeah.
And so if you take in, this actually almost would have fit into one of the chapters in this book, although it'll be in the next one. But so if the government taxes 0%, so we're like over here. No money. I have to write this out. But if the government doesn't apply a tax, if the tax is 0%, then you wind up with no revenue because that's how money works.
Joanne, this is how you can tell actual mathematics.
Wow.
They resort to the napkin instantly.
Yeah, exactly. And engineers too. Every engineer has drawn me a graph, regardless.
And then if you tax 100%, similarly, you're going to wind up with no money. This is more debatable, but arguably the grounds is that, like, if you tax 100%, no one will work because they don't get to keep the money. Or if they do work, they'll work kind of on the black market, and so you just won't. They won't report to the government. You won't collect anything. So that's sort of revenue. Sorry, writing. Okay, let's see if this actually works. So that's like the basic idea, right? Those kind of 2 points I've drawn on the bottom. If you have 0% tax rate, then you collect nothing. If you have 100%, you collect nothing. And so in theory, right, if you start charging more than 0 or less than 100, now you start to get some revenue. So Arthur Laffer concludes, drawing his diagram sideways, unlike mine, because economists are weird, sideways, crab-walking people. Right, somewhere there must be this maximum point, which that's where the government gets the most revenue it can, right? If it starts charging any more, then like people stop wanting to work and the government loses money. And Laffer's point is you never want to be over here because anyway, which no one knew at the time where that point was or if we were anywhere close to it. But so it's just like such a cute little graph, and like you can draw. There's a quote, some economist, I'm forgetting who, but said the nice thing is you can explain it to a congressperson in 6 minutes, and they can talk about it for 6 months. So it's like as much as anything, it's like a fairly simple piece of economics, but it's a really good piece of political messaging, a very potent, which had enormous, like multi-trillion-dollar effects on the U.S. economy.
So we're at the top of the hour, and so this has been a great conversation with Ben Orlin, who is the author of Math with Bad Drawings, and also he has a blog by the same name. And apparently has another book that will eventually come out, right? Probably another year or so.
Yeah, exactly.
Okay. Yeah. Oh, I'll be looking forward to it. Now, is it going to have drawings?
Oh, definitely. Yeah,
okay. Okay. All right. So it's like Math with Bad Drawings 2?
It's well, I've been talking about much. It's Change is the Only Constant is the title.
Okay.
Or Math with even worse drawings. Perhaps.
Yeah, with that. Math with drawings have deteriorated even. Yeah, no, thank you both so much. It's been really fun for me.
Yeah, great. Thank you for joining us today. And of course, Jeff, always happy to, get your physicist mathematical perspective.
Yeah, thank you, Joanne.
Okay, we'll see you next time on Read Science.